All right, so let's take a look at this warm up here. It's got a little bit of pretty much everything we've done so far this year. So the first question says, determine if there are any outliers in each distribution. So we have to remember, how do we determine if there are outliers? All right, so the two rules that we have are Q1 minus 1.5 times the IQR, and Q3 plus 1.5 times the IQR. And then, in case you didn't remember, IQR is Q3 minus Q1. All right, now we have two distributions here, so we're going to need to do this twice. All right, so let's start with Stony Brook. So we'll start with Stony Brook here. All right, Stony Brook's Q1 is 3.5. So it's going to be 3.5 minus 1.5 times the IQR. All right, so we've got to subtract these two. 7.5 minus 3.5 is going to be 4. So 1.5 times 4. And then it's going to be 7.5 plus 1.5 times 4. All right. So 3.5 minus 1.5 times 4 is negative 2.5. 7.5 plus 1.5 times 4 is going to be 13.5. So we're looking, are there observations below negative 2.5? Which no, there are not, right? Because the minimum is 0. Also, we're like measuring something, so how would negative make sense? And the maximum is 12, so there's nothing above 13.5. So we can say that there are no outliers for Stony Brook. And then we're going to do the same thing for Millbrook. Now again, we're going to need the IQR. So 10.5 minus 4.5 is going to be 6. So Q1 was 4.5. So we've got 4.5 minus 1.5 times 6. Q3 was 10.5. So we have 10.5 plus 1.5 times 6. Let's see what we got here. 4.5 minus 1.5 times 6 is negative 4.5. So it's pretty clear we're not going to have any outliers on the low side because, again, we can't really go below 0. And 10.5 plus 1.5 times 6 is 19.5. We can see that the maximum is 20, and we actually have a dot there at 20. The next highest dot is 18. So this one would have one outlier, and it is at 20. All right, 20 is the only one that's an outlier. So down below, it says draw parallel box plots of these two distributions. Be sure to label the plots and provide a scale. All right, so I'll make my scale down here. And let's say I'll go by 2s. So 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and then 20. All right, so if I look at the first one, I'll do Stony Brook first. Stony Brook's minimum is at 0, so its tail is going to go to 0. Its quartile 1 is at 3.5. So I'm going to start my box right about there. All right. My box's dividing line is at the median, which is 5. So there's that. Quartile 3 is at 7.5. So I'll go just a little before the 8 there. And then the max is at 12. So I'll mark that right there. And again, I'm just going to write next to this that this is the Stony Brook graph. So I'll just put an SB there for Stony Brook. And then parallel means I'm going to put the other one right on top of that. So this is going to be the Millbrook graph. Now, Millbrook still has a minimum of 0. All right, so I'm going to start it right there. Now its Q1 is at 4.5. So let's start the box a little after the 4. All right, the median is at 8.25. So let's go and make the dividing line just a little bit after the 8. All right, quartile 3 is at 10.5. So again, my box will end a little after the 10 there. And then this is the part where I have to be careful. All right, 20 is an outlier. The largest non-outlier is right here at 18. So my whisker is only going to go to 18. I'm going to stop it right there. And then I'm going to put an asterisk at the 20 to designate that it's an outlier. And then again, I'm going to put the little MB here to say that that's Millbrook. Okay? So again, this is from Unit 1, but just making sure you know how to detect outliers and then making sure that you represent them correctly on a graph. All right. Jax loves to go muskrat hunting instead of taking statistics class. This problem may or may not be about a former student. In 2016, Jax bagged an average of 6.5 muskrats per outing with a standard deviation of 1 muskrat. In 2017, his average was 5.2 muskrats with a standard deviation of 2 muskrats. Oddly enough, on November 7th of both years, Jax bagged 10 muskrats. It's a weird question, I'll admit it. In which year, 2016 or 2017, was this November 7th performance more impressive compared to the standards he set for himself? All right, so when we have two different distributions and we're trying to compare them, the only way that we know to do that right now is through z-scores. All right, so what we're going to do is we're going to calculate a z-score for 2016, we're going to calculate a z-score for 2017 and see which one is better. All right, and just remember that the formula is observation minus mean divided by standard deviation. All right. So if we look at 2016, all right, 10 is our observation. The mean in 2016 was 6.5. The standard deviation was 1. All right. So 10 minus 6.5 is going to be 3.5. Divided by 1 is still going to be 3.5. So that's 3.5 standard deviations above the mean. All right, that's what the z-score tells us. Standard deviations above the mean. In 2017, the observation is still 10 because it told us he got 10 in both years. But now the average was 5.2. The average was a little lower, but the standard deviation was higher. So 10 minus 5.2 is 4.8. And then if we divide 4.8 by 2, we're going to get 2.4 standard deviations above the mean. So even though he was further above the mean in 2017, that's sort of counteracted by the higher standard deviation. So 2016 is more impressive because it is more standard deviations above the mean. All right, so that makes it a more impressive performance. All right, but knowing how to calculate z-scores, obviously something we've been doing, something you're going to need to be able to continue to do. In a study of relationship between the amount of violence a person watches on TV and the viewer's age, 81 regular TV watchers were randomly selected and classified according to their age group and whether they were low violence or high violence viewers. Here's a two-way table of the results. Calculate 3 conditional distributions for violence watched, one for each age group. All right, so the conditional distributions for violence watched, so that means our percentages should be dealing with percent low and percent high, because our distribution is on the violence category, not on the age category. So what we're going to do is we're going to limit ourselves to a specific age, and we're going to say, all right, for 16 to 34, what percent watched low violence, what percent watched high violence. So we're going to limit ourselves to a single column each time. So low for this one would be 8 out of 26, which as a percentage is, I'm just going to keep this simple and say that it is 0.31 or 31%, which means high is 18 out of 26, which should be, and I guess I'm just confirming, 0.69. All right. Then we would just go and repeat the process. All right. So for 35 to 54, what percent are low violence watchers? What percent are high violence watchers? So this one would be 12 out of 27 and 15 out of 27. 12 out of 27 is basically 44%, 0.44. 15 out of 27 then should be 56%, and it does round that way, so 0.56. And then last but not least, 55 plus, we're figuring out the low and the high. So low is 21 out of 28, which is 3/4, which means it's 0.75. And then it's 7 out of 28, which is 1/4, or 0.25. All right, so this would be the conditional distribution of violence watched, one for each age group. All right, remember the distribution is made up of several percents. So there's my distribution for this age group. There's my distribution for this age group. There's my distribution for this final age group. All right, last but not least, researchers in Norway analyzed data on birth weights of 400,000 newborns over a 6-year period. The distribution had a mean of 3,668 and a standard deviation of 511. Babies that weigh less than 2,500 grams are classified as low birth weight. So what percent of babies will be classified as low birth weight? We're basically saying what percent is underneath 2,500, but we have to start by turning 2,500 into a z-score. We want to know, well, all right, in terms of standard deviations, how far above or below the mean is that value? So 2,500 minus 3,668 divided by 511. So if we do that here, 2,500 minus 3,668 divided by 511. So that value is, I'm just going to go to the 100th here, negative 2.29 standard deviations below the mean. So what is that as a percentage? All right, if we visually think about it, we know that it's not going to be very big because we're down here in the smaller part of our curve. And if we want to know the exact value, we would say negative 9,999 to negative 2.29 when the mean is 0 and the standard deviation is 1. All right, so normal CDF, negative 999, negative 2.29. When the mean is 0, the standard deviation is 1. And we are going to see that that's a pretty small value, 0.0110, or we can write that as 1.10% are going to be classified as low birth weight. All right, the last question says find the quartiles of the birth weight distribution. So the quartiles are the numbers that divide your data into 4 equal parts. So those numbers are Q1, Q2, which we usually just call the median, and Q3, right? Those are our quartiles. So we're going to start by finding the z-scores that correspond to each of those quartiles. So that means we're going to need to do inverse norm of 0.25 when the mean is 0 and the standard deviation is 1. We're going to do inverse norm of 0.5 when the mean is 0 and the standard deviation is 1. And we're going to do inverse norm of 0.75 when the mean is 0 and the standard deviation is 1. So for each of these, we're just going to go to that second distribution menu or second vars, which brings up the distribution menu. Inverse norm of 0.25, mean of 0, standard deviation of 1. And we've got to get all 3 of these. So this first one we'll say, we'll just go to the 100th place for each of these, negative 0.67. All right, the next one, right, inverse norm. Now, we should know this one before we even do it because we're saying 50% of the area. So 50% of the area is right in the middle, which means we should be getting a z-score of 0. And we are. And then 0.75, we should also know this one because the distribution is mirrored. So 0.75 is the reciprocal of 0.25. So we should get a positive 0.67. And if we put that in there, 0.7501, there's our positive 0.67. All right. So these are the z-score cutoffs, which again are standard deviations. So standard deviations above or below the mean. Now we just have to figure out what they are in terms of actual observations. So we use the z-score formula in reverse. And we say, all right, our observation is what we're solving for. Our z-score is negative 0.67. Our observation is what we're solving for. Our mean is 3668. And our standard deviation is 511. Now this middle one here, I don't even have to do because the mean is, the z-score is 0. So a z-score of 0 is saying you are 0 standard deviations from the mean, which means the observation has to be the mean itself. So that's 3668, right? This would be our Q2. And then this one, I do have to do 0.67 equals x minus 3668 divided by 511. So again, just moving to our calculator here, I've got negative 0.67 times the 511 plus the 3668, and I end up with an x of 3325.63. So x equals 3325.63. All right, and this is my Q1. All right, so that's my first quartile. That's my median. All right, let me put that median. Because remember, when things are perfectly symmetric, the mean and the median are the same, which in a normal distribution is perfectly symmetric. So the median and the mean are exactly the same. And then in the last one, it's just positive 0.67 times the 511 plus the 3668, which is 4010.37. So x equals 4010 or 4010.37. And again, this would be my Q3 value. All right. So again, just using sort of NCDF, using inverse norm to find different values. And then we've also got our, conditional distributions. We've got our outliers, box and whiskers, z-scores. So this is kind of like a nice summary of everything we've done so far. All right. So hopefully this was familiar and hopefully this video was helpful. All right. Have a great day.